I welcome you for this presentation. In this presentation, we are going to discuss about public key crypto systems 1. Why I have given public key crypto systems 1 means in the next presentation also we are going to discuss about other public key crypto systems. So in this presentation, we are going to discuss about Diffie-Hellman key exchange, then a Diffie-Hellman setup, then Diffie-Hellman example, then key exchange protocols, then this Diffie-Hellman key exchange crypto system is vulnerable to man in the middle attack, then Elgamal cryptography, then Elgamal message exchange, then one example for this Elgamal crypto system and summary of this presentation. So this is about the introduction to Diffie-Hellman key exchange. That is, this is the first public key scheme proposed. That is, this Diffie-Hellman only introduces this public key scheme. That is, earlier we had only private key cryptography. So with the help of two keys, we can perform the encryption as well as decryption. That process was published by Diffie and Hellman only in 1976. Along with the exposition of a public key concept. So public key, the foundation of this public key cryptography is based on this Diffie-Hellman key exchange only. And now known that Williamson, that is UKCESG, secretly proposed the concept in 1970. It is proposed by Diffie and Hellman in 1976, but they are telling that secretly, Williamson proposed the same concept in 1970, and this Diffie-Hellman key exchange is the practical method for exchange of secret keys. So, if we want to exchange a key between two parties, then we can go in for this Diffie-Hellman key exchange. But this key exchange process crypto system is for only exchanging the keys and not for exchanging the messages. And nowadays also this Diffie-Hellman key exchange crypto system is used in many commercial products. So in most of the cryptographic applications or products that use cryptography, they mostly use this Diffie-Hellman key exchange crypto system. So this Diffie-Hellman key exchange is a public key distribution scheme. So this this crypto system can be used to exchange the keys and cannot be used to exchange any arbitrary message. That is very, very important. Rather, it can establish a common key. So here a common key is established and it is shared. That common key is known only to the two participants. Whoever the sender and the receiver, they only know about that common key. So that we will be discussing later. So here the value of key depends on the participants, that is their private and public key. Based on the private and the public key information, the key depends. So here we are using the exponentiation in Galois field, that is a modulo, a prime or a polynomial. So this exponentiation process is easy to compute. But another thing, the main security relies on the difficulty of computing the discrete logarithms. Here discrete logarithms are also involved. So this discrete logarithm is very hard to perform or hard to compute. In the RSA crypto system, instead of discrete logarithms, we had a factoring problem. That factoring problem is hard in RSA crypto system, but in this Diffie-Hellman key exchange scheme, this exponentiation part is easy, similar to that of RSA crypto system, but the discrete logarithm part is very difficult or hard to compute. So the security lies in this discrete logarithm computation only. So the cryptanalyst will face very difficulty while you are computing the discrete logarithms. But if you want to make the system in a very secure manner, we have to use very large numbers, so that it makes the cryptanalyst to perform more computation, and sometimes practically it is infeasible to extract the information also. So this is the basic structure of this Diffie-Hellman key exchange. That is how the process, the flow of this Diffie-Hellman key exchange process. First here, Alice is the sender and Bob is the receiver. We assume that. So Alice and Bob share a prime number P. Prime number not P, it is prime number Q and alpha, such that alpha less than Q and alpha is a primitive root of Q. So first Alice and Bob are selecting a prime number Q. So this side also the same explanation is given. So Alice and Bob share a prime number Q and alpha must be less than Q. So alpha is the primitive root of Q. So we have to know what is the primitive root. So alpha must be a primitive root of Q. Likewise, we have to choose the value of Q and alpha. The Alice and Bob has to choose. So Alice generates a private key XA such that XA less than Q. Here what is Q? A prime number that is shared by both Alice and Bob, that number. So the Alice generates a private key XA such that XA less than Q, and parallelly Bob generates a private key XB such that XB less than Q. Then Alice calculates a public key YA. How Alice is calculating the public key? Using the alpha value. It is a common value, but XA is private to Alice. So alpha power XA mod Q. Here alpha and Q are known to Bob also. Only value not known by Bob is XA. Similarly, this side Bob is calculating a public key YB equal to alpha power XB mod Q. So here also XB is the private key that Bob generates, that is not known by Alice. But alpha and Q are known by Alice also. So with the help of alpha, Q and the private key XB, Bob is calculating the public key YB. After calculating YA and YB, Alice is sharing that YA to Bob, and Bob is sharing the YB to Alice. So Alice receives Bob's public key YB in plain text and Bob receives Alice public key YA in plain text. Then they are using that value to compute a shared secret key K. This shared secret key K is used as session key. So Alice calculates a shared secret key K equal to YB, whatever received from Bob, YB power the private key XA mod Q. Likewise, Bob also calculates a shared secret key K equal to YA power XB mod Q. So here the explanation is given, that is all users agree on the global parameters. Here global parameters are Q and alpha. It is not A, it is alpha. And each user A generates their key, that is chooses a secret key number XA less than Q and compute their public key YA equal to alpha power XA mod Q. And each user makes public key YA. Whatever we seen in the pictorial representation, same is given here. So the shared session key for users A and B is KAB. In the last step, Alice and Bob computes a shared secret key K, that is KAB. So KAB equal to alpha power XA into XB mod Q, that is YA power XB mod Q, which B can compute, and YB power XA mod Q, which A can compute. So KAB is used as session key in private key encryption scheme between Alice and Bob. So if Alice and Bob subsequently communicate, they will have the same key as before unless they choose a new public key. So always they have to choose a new public keys. Suppose they are not using this new public keys and they are using the same, they have the same key as before only. So if they are not choosing the new public keys. So attacker needs an X value and X must be solved using discrete logarithm. So this computing the X value using discrete logarithms is very difficult. It is a hard problem. So this Diffie-Hellman key exchange process is somewhat secure because X value is difficult to compute. But this Diffie-Hellman key exchange is vulnerable to another attack also, that is meet in the middle attack or man in the middle attack. So here we are, one example is given, whatever we discussed earlier, the same things are applied here, that is users Alice and Bob who wish to swap keys. That is why it is given as swap keys, because they are exchanging the keys. So in order to exchange the keys only, we are having this Diffie-Hellman key exchange crypto system. So if they want to swap the keys, what are the steps involved to swap the keys? That only we are going to see. So here they are agree on the prime number Q equal to 353. Here for this example, because we need to compute manually, so that here three small numbers are given. But in the practical cases, if you are applying this crypto system in some commercial products, there we have to use very large prime numbers. So always you have to keep this in mind. And equal to 3. And choose random secret keys XA equal to 97 and XB equal to 233. Then the public keys are computed. Alice compute YA, that is 3 power 97 mod 353 mod Q 353, that is 40, and YB equal to 3 power 233 mod 353, that is 248. You please work out and verify that whether you are getting the same answer for this. Then compute the shared session key as KAB equal to YB power XA mod 353, that is what is YB? It is 248. What is XA? It is 97 equal to 160. Alice got. Then KAB equal to YA power XB mod 353 equal to 40 power 233 equal to 160. Both K values KAB and KAB is 160. So the session key is generated by both Alice and Bob. Whatever the exchange process happens, with the help of the exchange process, they have generated a session key. Both the keys are having the same value. That is very, very important. So in order to compute the same key value, they have followed that much steps, key exchange problem. Finally, they got the key K equal to 160. So here this key exchange protocols, if the users could create random private or public Diffie-Hellman keys each time they communicate, or the users could create a known private or public Diffie-Hellman key and publish in a directory, then consulted and used to securely communicate with them. In both the cases, first as well as the second case, this Diffie-Hellman key exchange is vulnerable to meet in the middle attack. So authentication of the keys is needed. Meet in the middle attack or man in the middle attack. So in between Alice and Bob, some intruder can intercept all the conversation and he can collect all the information also. Let us see that how the meet in the middle attack happens in this Diffie-Hellman key exchange crypto system. So here, man in the middle attack. So Darth prepares by creating two private keys. Who is Darth here? Because we know Alice and Bob. Alice is the sender and Bob is the receiver. Likewise only we have discussed earlier in the Diffie-Hellman crypto system. Who is Darth? Darth is the attacker or the cryptanalyst. He is the cryptanalyst or attacker or opponent. So Darth is the culprit here. So Darth prepares by creating two private or public keys and Alice transmits her public key to Bob. So what is the first step? The Alice has to transmit her public key to Bob. And in that place, in between, Alice is here, Bob is here, in between Darth is there. So Darth is creating two private as well as public keys because both the sides he has to play. So he created two private and public keys. So after Alice transmits her public key to Bob, what Darth is doing? Darth intercepts this and transmits his first public key to Bob because he created two public key. So first public key he is transmitting to Bob. Darth also calculates a shared key with Alice and Bob receives the public key and calculates the shared key with Darth instead of Alice, and Bob transmits his public key to Alice. So Darth again intercepts this and transmits his second public key to Alice and Darth calculates the shared key with Bob. So Alice receives the key and calculates the shared key with Darth instead of Bob. So both Bob as well as Alice is thinking that Bob is thinking that he has received everything from Alice and Alice is thinking that she received everything from Bob. But that is not the case. Both of them received everything from Darth. Okay. So Darth can then intercept, decrypt, re-encrypt, forward all messages between them. So whatever the work Darth wants to do, he can perform everything because he is playing the role of both Alice as well as Bob. So in between he is sitting and playing the role of both Alice and Bob and making Alice and Bob that they are having a secure communication, but that is not the case because in between Darth is there, Darth only doing all the work. So this Diffie-Hellman key exchange crypto system is vulnerable to man in the middle attack. So this is the pictorial representation of man in the middle attack. So Alice we know, Bob we know, in between Darth is there. So Dart is generating 2 private keys and 2 public keys, and whatever the conversation he wants to do, he is doing with Alice as well as Bob. So first Alice is sending the YA to Bob, but Dart is intercepting everything, and he is just sending YD1 to Bob and YD2 to Alice. So Alice and Bob are working on whatever the values received from Dart and not from Alice or Bob, the other side. Okay, so they are thinking that they are working with in a secure environment, but that is not the case. And finally, they share Alice and Dart share K2 and Bob and Dart share K1. But what they want to do, they can't give it this to key to Dart, but actually Dart is collecting all the keys from Alice as well as Bob. So whatever the communication happening between Alice and Bob, everything can be intercepted by Dart. So this crypto system is vulnerable to man in the middle attack. Another crypto system is Elgamal Cryptography or Elgamal crypto system. So this is also a public key crypto system related to the Diffie-Hellman. This crypto system also uses exponentiation in the finite field, that is GF of Galois field of P only, with a security based difficulty of computing discrete logarithms similar to that of Diffie-Hellman. Here also the difficulty is in computing the discrete logarithm. So user A generates their key, that is user A chooses a secret number, that is XA, that lies between 1 and Q minus 1. Here also the same global parameters are there. What are the global parameters we are having there? Q as well as alpha. So Q and alpha are the global parameters. The same Q and alpha are used in the Elgamal crypto system also. Then the public key is computed using YA equal to, it is alpha power XA mod Q. Then Bob encrypt a message to send to A computing, that is represent the message M in a range 0 to Q minus 1. So M lies between 0 to Q minus 1. That is longer messages have to be sent as blocks. So if you are having longer messages, we have to split it into blocks, and then only we have to send those messages. So here we have to choose a random integer K, that K lies between 1 and Q minus 1. Then we are computing a one-time key, that is capital K. This K and this K are different. This is small k, then one-time key capital K. How we are computing the capital K? With the help of a small k. So equal to YA power K mod Q. Then we are encrypting the message as a pair of integers. This crypto system is somewhat different compared to other crypto systems. In other crypto systems, we are encrypting a message and we are getting a ciphertext as one another message only. But here we are getting a pair of ciphertext where C1 equal to A power K mod Q and C2, it is not A, it is alpha power K mod Q, and C2 equal to Km mod Q. K is a one-time key, Km mod Q. A then recovers message by recovering key K as K equal to C1 x power A mod Q, and computing the message M equal to C2 K inverse mod Q. So K inverse you need to find. So a unique K must be used each time, otherwise result in insecure. So always the K value, that is the random integer K value, we have to use each and every time. If you are using a unique value, then this Elgamal crypto system is secure, otherwise it is vulnerable to some attacks. So this is the summary of that. Because we are having the global parameters, then Alice is generating the public key, then the encryption process is performed by Bob with the help of Alice public key. So here we are having the plain text M, it is less than Q, and we are selecting a random integer K, K less than Q. Then using this K value, one time key K is computed, that is K equal to YA power K mod Q. Then the ciphertext pair C1 and C2 are computed using this formula, that is C1 equal to alpha power K mod Q and C2 equal to Km, one time key M mod Q. So we are getting the ciphertext C1 and C2. So the decryption is performed by Alice with the help of Alice private key. So we are having the ciphertext C1 and C2. So Alice has to calculate the K value, that is K equal to C1 power XA mod Q. Then the plain text M is obtained using C2 into K inverse mod Q. So likewise, the encryption and decryption process is performed in Elgamal crypto system. Let us see one example. So here, in this example, we have used Galois field of P, that is Galois field of 19. That is the prime number Q equal to 19 we have used, and the alpha value is used as 10. It is not A value, it is alpha value equal to 10. And Alice computes her key, that is A chooses XA equal to 5 and computes YA equal to alpha power XA mod Q. So 10 power 5 mod Q, that is mod 19, that is 3. Then Bob sends a message M equal to 17. Here the plain text is 17, but it is received as a ciphertext pair of 11, 5. So 17 is received by the receiver by 11, 5 as a ciphertext pair. Then a random number K equal to 6 is chosen. Then one time K is computed, that is K equal to YA power K mod Q, that is 3 power 6 mod 19, which is equivalent to 7. You please work out all these calculations and you verify whether you are getting the same answer or not. Then computing C1 equal to alpha power K mod Q equal to 10 power 6 mod 19 equal to 11. Then we are having the C2. C1 value is 11 and C2 equal to Km mod Q, that is 7 into 17 mod 19, which is equivalent to 5. So only we are having the ciphertext pair as 11 and 5. Then Alice recovers the original message by computing recover K equal to C1 power XA mod Q equal to 11 power 5 mod 19, that is 7. Then compute the inverse K inverse equal to 7 inverse mod 19, that is 11. And recover M equal to C2 K inverse mod Q, that is 5 into 11 mod 19 equal to 17. So after a decryption process, the message M equal to 17 is obtained. So in this presentation, we have discussed about two famous public key crypto systems. One is the Diffie-Hellman crypto system, a public key crypto system. Key exchange, it is mainly for key exchange, not for the message. And another one is Elgamal crypto system. And this Diffie-Hellman key exchange is vulnerable to man in the middle attack. That also we have discussed. And with respect to these two crypto systems, we have discussed one example for each of the crypto systems. So in the next presentation, we will be discussing about another crypto system, that is elliptic curve crypto system. Thank you.